Welcome to this podcast on development of a post-dielectric barrier discharge plasma reactor for the treatment of simulated dye wastewater.
That's quite a title. But the problem it addresses is significant. Textile industrial wastewater, laden with toxic dyes, poses a major environmental challenge.
Indeed, this paper explores non-thermal plasma as an advanced oxidation technique. It aims to mineralize wastewater without needing external chemicals.
Essentially, plasma creates highly reactive species. These can break down complex organic dye molecules into less harmful compounds, right?
Precisely. The key innovation here is a novel post-dielectric barrier discharge or DBD plasma reactor. It features a liquid electrode.
What does post DBD mean for practical use? Does it improve how the plasma interacts with the water?
Yes, it overcomes the limited plasma water interaction of simple DBD reactors. This design disperses oxidizing species as bubbles in the wastewater.
So, they built this reactor. What did they test its effectiveness on?
They primarily used crystal violet dye solution as a model for simulated dye wastewater. They also tested methyl blue, reactive red 120, and methyl orange.
And how did they measure the degradation of these dyes?
They monitored dye degradation using UV spectroscopy. This technique tracks the decrease in dye concentration over time.
What were some initial findings about the reactor setup? Did the liquid electrodes' conductivity matter?
Interestingly, the degradation rate was independent of the liquid cathode's electrical conductivity, varying from 300 microsiemens per centimeter to 4.2 millisiemens per centimeter.
That's a wide range. Did they optimize other physical aspects of the reactor?
Yes, increasing the DBD plasma volume by fully immersing the dielectric tube reduced degradation time by 20 to 25%.
What about the water itself? Did using tap water with its higher mineral content affect the results significantly?
Using normal tap water only required about 10 to 15% more time for degradation compared to distilled water. The effect was not substantial.
They also looked at the oxygen flow rate, didn't they?
They observed an exponential decrease in degradation time with increasing oxygen flow rate up to 500 milliliters per minute. Beyond that, the effect slowed.
Why did it slow down after 500 milliliters per minute? Was it less efficient?
Larger gas bubbles formed at higher flow rates. This reduced the total surface area for mass transfer of reactive species into the liquid.
And stirring the solution? Did that help?
Stirrer speed linearly decreased degradation time. For example, at 400 rpm, mixing and diffusion of reactive species improved significantly.
So, more stirring means faster degradation. What about the initial concentration of the dye?
We found a nearly linear relationship. Doubling the dye concentration, say from 20 to 40 milligrams per liter, roughly doubled the degradation time.
Does the temperature of the dye solution impact the degradation rate?
Yes, degradation was 25 to 30% faster in cold solutions around 20 degrees Celsius compared to hot ones at 80 degrees Celsius.
That's interesting. What about the pH of the solution?
An acidic environment like pH 2 showed a 20 to 25% faster degradation rate compared to a mildly basic pH of 8.
So, the kinetics were pseudo first order and it's quite efficient, right?
Indeed, they achieved over 90% dye degradation in just 4 minutes. More than 98% was reached within 6 to 7 minutes.
This work truly highlights the potential of plasma technology for tackling industrial wastewater pollution. It's an important step towards cleaner water.